end. So these are the topics that we're going to be discussing this evening. It's a huge program, and I've got to limit things just to get through it all in the allotted time. So we'll be talking about the status of our program. We'll be looking at our look ahead. We'll talk about the components of the high-speed rail, some of our technical challenges, and some of our lessons learned to date.
And I just want to add that now we are being recorded. So sorry, I just want to add that in while we're being recorded. Thank you.
So in order to give you a status of our programs, it's important to first describe the program and the project. Our program is really just one large project in reality, or a series of projects that link together to form the end state, which is a functioning high-speed rail system that extends from San Francisco to Los Angeles, which is 494 miles. And we've got obviously this is our mission, which is to design and construct the high-speed rail. We've got design speeds actually up to 220 miles an hour operating speed, with design speeds that exceed that up to 250. We've got phase one is the first 494 miles, which goes San Francisco down to Los Angeles. And then after phase one is complete, there's a potential to do phase two, which is a 300-mile extension, which is really two parts. It's Merced up to Sacramento, and then Los Angeles down to San Diego as a phase two. Now, the progress that we've made to date is that we've got 380 miles environmentally cleared. So that's Bay Area, San Jose, LA County, Palmdale area, and obviously the areas that we're constructing in the Central Valley. We've got 119 miles that are under construction. That's this section in the Central Valley, which extends from Merced down to just north of Madera, just north of Bakersfield, which is, we refer to that as Poplar Avenue. We've got a commitment to complete Merced down to Bakersfield. So that's an extension that would involve some additional design work and construction work to get the full Merced to Bakersfield commitment obtained. We've also got Caltrain electrification construction underway, which is part of our grant deal, is to electrify Caltrain. That's up in this northern region up here. That's underway. And then we've also got a funding commitment for the LAUS improvements. LAUS is the Los Angeles Union Station down in Los Angeles. And then we're also looking at advancing station planning, particularly for stations that are, for obvious reasons, down in the Central Valley region in this area. Our program isn't just related to the end state of a high-speed rail. The benefits go beyond that end state. There's benefits all along the way. There's jobs that are being created in the construction area, as well as other areas of the program. We're employing 698 small businesses. We've got DBE and DVBE businesses involved. And then there's also a commitment to the environment with 100% electrification based on renewable energy. And we're currently using Tier 4 equipment. Tier 4 is the grade of the EPA's emission standards. It's the new standards that new heavy equipment diesel engines must meet. All of our equipment is using Tier 4 equipment. And there's a commitment that we're going to be reducing VMT. VMT is a vehicle miles traveled, which is basically taking cars off the road. It's a useful summary of a metric of measuring a project's impact on a jurisdiction or region. off the road. So it's not just about a high-speed rail. It's about everything along the way to that end state. So now we'll get into description of the different regions. We've really got three regions. We've got a northern region, we've got a southern region, and then we have a Central Valley region. So I'll start with the north and the south, and then head into the Central Valley. So the Bay Area is up in the north, and that's 159 miles. We've environmentally cleared the entire stretch, and it's eligible to begin advanced design in fiscal year 2022-23. We've got, as I mentioned earlier, we've got the corridor electrification underway in the north region for the Caltrain corridor. And however, the segment construction is still unfunded to date. Our goal is to advance the design work, to do advanced design work in 2023, and to take a look at targeted early right-of-way, which I'll get into that a little bit later, and identify shared corridor early capital investments that can be started, and then we've got to work on developing funding plan options as we progress. The Southern California area is very similar to the northern area. However, only 92 miles of the 164 miles have been environmentally cleared, so we have a bit more to do on that. It's about 50%. The target is that we'll clear the remainder in 2023, 24, the next year and a half or two. Some advanced design could also begin in 2023, and I mentioned the LA Union Station that's fully funded, and it's cleared environmental this year. And again, the segment construction for that region is also unfunded. The goals are the same in the southern region as far as completing the environmental and beginning in advanced design 2023. Same sort of goals that we have in the northern region. So then we get into the Central Valley, and this is where a lot of all of the construction is occurring in the Central Valley right now. So this gives you a feel for where we are with the various different aspects of the program in the Central Valley, and this is construction package 1. Construction package 1 is, there's 3 construction packages in the valley, and they basically work from that northern section, which is up in Madera, starts up there in the north in Madera, and it stretches down to the Fresno area. CP23 is the second one. We combined 2 construction packages into one and call it CP23, and that is the Fresno region down into the valley a little further down. And then CP4 is the southernmost portion that takes us all the way into Poplar Avenue. So you can see that we've got pretty much, the design is pretty much complete. We've got 95% of design complete. The parcels have been delivered. There's still some work, a little bit to do, but not much. Utility relocation is still underway, and most of the structure work has been done. And this is an example right here of one of the structures. It's a Tulare Street underpass that's going under our alignment. And we've got 50% of the guideway complete or in progress. And we're 66% of our contract. That's CP1, that's the north end. Then we get to the middle section, which is CP23. This one, most of the design is complete as well. Most of the right-of-way is delivered. Utility relocation is about the same. The structures construction is a bit behind the CP1. They're at 60%. It started after CP1 as well, so that kind of explains some of that. plus some of the other issues that we've had to contend with in the valley. It's a much bigger section down there. And then we've got 74% of the guideway complete or in progress. And we're at about the same for the overall contract spending. So this is a look at CP4, and this one we're farthest along with this one. The design is completely done, 100%. The right-of-way parcels are at 82%. The utility relocation is much further along, and then you can see the structures and the guideway completion is also in really good shape. That's the smallest of the three CPs. So let's take a look at some of our construction that you can see is ongoing and completed work. A lot of this is in CP1. This is a tight arch structure in CP1, and you can see that's one of our complex structures that we have. You can see another one. This is not a tight arch. It's an offset arch. This is in downtown Fresno, and it's underway in construction. That one has been a long time coming. Some of our challenges that we've had in getting construction moving are related to the usual culprits, which are the third-party agreements, utilities, identification and relocation. Those are the two really big areas. Right-of-way acquisition is also a key factor, a critical success factor that we have in getting to construction and getting construction complete. These are what we call a type 2 overhead structure. So that's your typical overpass. Our alignment is down adjacent to these BNSF UP lines that are existing. So ours is that bare dirt area is where our rail will be going. And you can see there's a canal that's also part of that's considered a utility type project. Then we've got a pergola type structure here at Conejo Viaduct. This is one of our viaducts that has 3 different types of construction along the way. Gives you a little bit bigger view of that, but they're working on the pergola structure right there, and that's a good structure. We've got a couple of viaduct structures. This is a tub type structure that they're working on. It's a U-girder type construction. It's a nice design. It helps you to lower the profile as you cross over that overcrossing. Here's another pergola that's down there by Wasco, which is down there in CP4. So you can see that middle section right there is where our rail will be going. It's a slab track that runs over the pergola structure. This is an overpass, typical overpass with an open abutment type of design. We've got a couple different abutment types going on in our project. So that kind of gives you a feel for the types of bridge work that we're working on, and gives you an idea of some of the progression. So this is the look ahead. So we're looking to obviously clear the environmental work for the entire 494 miles, 500 miles to round it up. Work on the advanced, the engineering and design work where we can, we've got environmentally cleared statewide. We need to work on funding, obviously. We need to obviously deliver the electrified track. So right now, as you can see, we're working on civil infrastructure, which is going to support the track. So we've got another contract that we'll have to put out that will lay the track in the valley, and it will also have the overhead catenary system for the electrification among other areas in order to get a functioning train on that infrastructure. And then obviously we need to develop the funding strategy to extend beyond the Central Valley as soon as possible. So I thought I would talk a little bit about the components of the high-speed rail, because it kind of ties into some of our challenges and some of our lessons learned. So we've got embankment and transition zones. We've got bridges and viaducts, tunnels and trenches, intrusion protection, retaining walls, stations, and maintenance facilities. And then we've got tracking systems. This is going up from the civil infrastructure. And then we've got a ballasted and track slab form. We've got OCS, which I talked about, and then we've got the rolling stock and train control. There's a couple unique things. Our transition zones, that's where you're on the embankment and you're going to be going from embankment to bridge. We have to be very careful with that transition and make sure that we transition from a softer bed, if you will, for the embankment, and transition the stiffness of that bed to the stiffer abutment of a bridge. So that's a very special thing that you don't see too much concern with on highways, because they're not a steel on steel vehicle running 220 miles an hour. So there's a lot more sensitivity to a high-speed rail than there is to a car on a roadway, for example. And then we've got bridges. It's important to note the difference between what I would call a type 1 structure, which would be a structure that carries our rail, essentially, versus a type 2 structure, which is an overhead that goes over the track. And we may get into that a little bit as we go further. Over here, this is one of our bridges, if you will. That's a type 1 structure. It's carrying our track. So those viaducts we were looking at are type 1 structures. So let's get into a little bit some of these components. So this is construction package 1 and 2, 3. This is the same one. This is a viaduct bridge. This is just kind of an example of some of the viaducts that we have and the lengths of some of these. And these are not the longest ones, but we've got pergola, we've got tied arch, we've got skewed tied arches, non-tied staggered arches, we've got base isolation. It really runs the gamut on this program as far as the type of, we got precast I-girder construction, we've got cast in place box girders. So our structures really run the gamut. We've got type 2 structure would be like the Tuolumne Street bridge in Fresno, which carries two-way vehicle traffic. It's kind of your typical roadway bridge over our alignment. This picture, I don't know if you guys can see my mouse, but the picture on the upper right, it's got some examples, and the one on the right gives you a good combination of a type 1 structure, which is a trench going under a roadway in this case with our rail on it, and then a type 2 overhead structure bridge going over the top of that. So that's got a little combination of things going on there. The upper left one, or the left one there, that's got the tunnel, and then it's got the approach structure to it. We can get into the approach structure a little bit later, challenges related to that.
Brian, is it okay to ask a question right now?
Actually, yeah, I'm gonna be a little pressed for time.
Sure.
I can see. So
I can ask it later.
Okay, yeah, sorry about that. Just want to get through, and then we can get into the question and answer. Just take a note of that when we can come back. So this is type 1 aerial structure and a tunnel, and this is what I discussed in the previous slide. This one just kind of gives you an example of the varieties and long straddles, typical types of construction that we have in some of the lengths. Just an example. Here's a little bit more example of that. And this is preliminary, the PE per PD that stands for preliminary engineering for project development. It's a plus or minus 15% design stage. I don't know how visible this is, but you can see this structure's got, it's got a straddle bent. It's got over 3 mile lengths, outrigger bents. We have anticipated very, very tall columns for some of the approach structures as we approach the tunnels in the mountains. So there's going to be some serious challenges ahead. It's very exciting to get into that complex design. Here's a little bit more detail on the complex structures. One of the concerns for this particular structure, which may not be as much a concern for a highway structure, is the cap beam. If you got a drop cap or even an integral cap, superstructure movement is very important to limit with high-speed rail because of the speeds that we're traveling. So we have some pretty good limits on rotation and displacement that you wouldn't normally see on a bridge. That's one of the challenges that we have. And you know, stiffness is a challenge. You want to keep it, you don't want that bridge to move too much. So we have much stricter limitations on movements and stiffness than AASHTO for our high-speed rail bridges. A little bit more on complex structures. This is down in the Palmdale to Burbank section. You get some pretty tall piers. The track structure interaction is affected by the piers. When you get these tall piers, it's tough to keep that structure stiff. And we've got seismic performance of OBE versus MCE. I'll get into that a little bit later. This is typical cross sections of one of our bridge types, one of ours, which is a box girder construction. It gives you a slab track form here, and it shows sound walls and parapet walls, etc. on it. And it's a single cell box girder. A little bit bigger picture of that. We do have directive drawings. Right now we're design build is our philosophy. So we have some directive drawings that guide the designers, but it's designers' choice. We want to give them that flexibility for cost incentives, etc. So the complex structure design is site specific, and it's driven by the design build, which I was just mentioning. Some of the methods that we would expect to see explored would be accelerated bridge construction, segmental bridge. We've already seen some splice girder construction, movable scaffolding systems, and then we're looking for design and construction efficiencies. We are DB, there's pluses and minuses to that. Some of the methods are driven by different factors: cost, schedule, geometric limitations. Like when we saw the pergola structures, we were crossing at a skew over a railroad, so that led to a decision on a type of design and construction. Third-party requirements that kind of combines that. So here we can see some of our technical challenges that are related to the civil infrastructure design at bridges. And these are different displacement modes that we see. And this is rail. This is one of the reasons we have a particular concern that's more strict, I guess, than the typical roadway bridge. Again, we can't tolerate a lot of these types of movements as well as a roadway structure. So we've got for design criteria development, we have a seismic design criteria that's a maximum considered earthquake. We've got an operation-based earthquake. The operation-based earthquake is set up so that we can limit the effect of the earthquake on our system, so we can actually remain operational at a particular level of input. And that's really driven by displacement. And this often will dictate the design of the structure. It'll be the controlling load case for the design of the structure, not the maximum considered, not the big one, oddly enough. This is more on a no collapse, and I'll get into that a little bit later, but this is a 950-year event, and the OBE is more on the area of a 50-year to 100-year event. And then we've got tunnels, and these are the areas that I'll be looking at. Embankment and transition zones, really not focusing on, but subsidence and Rayleigh waves. We've also got hydrology is a big challenge. It's a normal challenge, I'll put it that way, but it is a challenge. I won't be really getting into that today. So this is our design criteria development. We started with the AASHTO LRFD with Caltrans amendments. We've got the Caltrans seismic design criteria, and then we're also applying AREMA, which is the rail requirements, ACI, AISC, et cetera. We're also, looking at UIC, which is the European code. We've got these as a basis, and then we get into our specific criteria development, and we look at international research, literature, other references, which I've already talked about, the UIC, et cetera. And then we've got our own project-specific parametric studies that we've done to establish our criteria. Our seismic performance criteria, we have a no collapse performance level objective for the big one, for the MCE event. It's a 950-year event, but we've found it's more moderate damage and life safety performance. It's better than no collapse, which is the typical bridge design criteria, is no collapse. So we're doing better than the typical bridge design, and that has a lot to do with our limitations for operations. It just leads to a much more robust structure. These are the limitations that I started to get into for the OBE event, and that's so we can maintain operations. So no derailment, obviously. You want to safely brake the train. We have automatic train control that'll be stopping the train. We have early detection, a lot of other areas, derailment protection with bogies, et cetera. That is part of that. We also, really don't want any damage at all or measurable long-term deformation. We can't afford to have rocking of bridge foundations, et cetera. So these are some of the areas for the OBE limitations. And then we get in for the MCE. It's a life safety, no collapse. However, it is leading, our criteria is actually beyond that. So it's more moderate. And obviously, flooding or mud inflow for underground structures, so the trenches and the tunnels, et cetera. Then we've also got to get our passengers off, so we have exiting requirements. I think I missed a. So this is a little bit more information related to the OBE event. The MCE really becomes a check because of the limitations imposed on OBE response. We do have a potential use of isolation bearings for capacity protection, which decouples the OBE event from the MCE event, so it does not become a driving factor. It usually, those limitations on displacement, et cetera, ends up resulting in a very, very large stiff column, and we have to perform a capacity protection for our foundation design or surrounding elements. And because of that OBE stiffness, it makes it very prohibitive to size up your foundation to accommodate the capacity protection. So we're looking at introducing something that no one else is doing, which is a potential use of isolation bearings for capacity protection. This is what I've already discussed. And then you know, again, the MCE has got a challenge. Because of our displacement based, you know, there's a challenge to the flexible. You want flexible columns for MCE. You want it to flex. But you know, the flexible columns give you a large deformation for OBE. So it's kind of a push me pull you. You want it stiff for the OBE event, but you want it flexible for the MCE. So we're trying to, it's a big challenge to try to get that balance when you get into the higher seismic regions and taller structures. So as far as our ground motions inputs, we've got program-specific ground motion procedures for design that we've developed. They're based on USERF 3, which is the Uniform California Earthquake Rupture Forecast. Version 3 is the current. We're actually ahead of the world with this in that we're making improvements on USERF 3. And then we've got the PSHA, which is the Probabilistic Seismic Hazard Assessment.
But I can't get it to do it.
If somebody's not muted. So for the final ground motions, you know, those are updated. So we do preliminary ground motions that we develop. Final ground motions are based on that preliminary information, and then when you get into final design, you update everything, and you propagate properly from the source to the site using these specific procedures. I can't get into a high level of detail. I'm really short on time. Sorry. So we've got ground motions at special sites, and those are where ground motion prediction equations can't be confidently applied. So you end up having to do site-specific. Those sites are locations that are subject to liquefaction, high nonlinear soil response. So you can have soil that's soft, sandy, varying conditions. A lot of river crossings will have that, and then there are site classes E and F, which are they're classified as sites that you need to do that. That's related to well, the CBC's got that. I think some of you would be familiar with that. And then we've got locations, all the locations where we've got the long span bridges, tunnels, underground structures, trench boxes, etc. So it's site driven and structure driven. Then we've got fault screening and displacement hazards. So we've got a lot of seismic faults in California, as you know. And so we have a process for screening the faults and hazard analysis with PFDHA, and then we've developed a program-specific procedure, PFDHA, in an effort to improve certainty. We're one of the sponsors for research at UCLA, in which they're compiling additional fault data for the PFDHA, and that's in order to get things more accurate, to get the most fault data that you can for input into that, to give you a better focus on your result. And the fault displacement zone it's a key factor because we've got a linear system, and we've got slip-related realignment that we have to do after an event, or even due to fault slip rates that just require us to realign occasionally. And because we're a linear system, you don't just look at a line as a fault as a line, you look at it as a zone. So this kind of gives you a feel for what we're looking at, and you can see this offset here in this area. So this is the fault displacement zone. It crosses all the way across here, and then this is the actual slip location. So this is a little bit more information on our criteria development. It's an 86% chance of exceeding in 100 years for OBE. That's a 50-year return period, as I noted earlier. We started with AASHTO and Caltrans requirements, and we added more restrictive amendments through technical and material specs. This is the MCE. So that's basically a 950-year return period. These are our conditions that we're looking for. Track structure interaction, ATC systems, that's automatic train control, early detection, derailment curves. And then we've got obviously the number one, well, number two. Safety is number one, passenger comfort is number two. Now we get into some tunnels. So this is a little picture of the major areas of tunnels that we have. So this is throughout the state. So we've got what's called the Pacheco Pass area. This is a blow up of that area, plus or minus 15 miles of tunnels, depending on the alternative chosen. This is the San Gabriel area, which is between Bakersfield and Palmdale. This is in the southern region, that's here. And this is also in the southern region, which is Palmdale to Burbank. And this has got the most challenging tunnels as we go under the San Gabriel Mountains. This is the Tehachapi here. This area, we're underneath the Angeles Forest, so that's going to be challenging from a third-party perspective. So it's important one of the important lessons learned or known things is the importance of getting geotechnical information early. So these are the areas that we're investigating. Gilroy to Los Banos is that Pacheco Pass region. Bakersfield to Palmdale is the Tehachapis, and then Palmdale to Burbank is the San Gabriel. And this gives you a picture. This is the Pacheco Pass area. I believe this is the Pacheco Pass. One of the big concerns down in the San Gabriels is we got a very high water head. We're pretty deep with the tunnel and the water is up fairly high. So there's going to be some challenges to tunneling through that area, particularly attaining a watertight condition because of the high water pressures. And so overall tunneling in variable geology is obviously a concern and a challenge. Seismically active areas with multiple fault crossings, that can lead to what we call fault chambers, which are widenings of the tunnel across that fault zone that are necessary for realignment of the track. We have incredibly large curves because of our speed and our requirement for passenger comfort. So when you need to realign it, you need a really long, maybe a mile-long fault chamber to do that realignment and put that curve in there after you have a fault slip. We have to do investigations on groundwater impacts. Permitting is always a challenge. Investigations in tunneling in environmentally sensitive areas, this being California, that's always a concern. And then we've got to perform expanded geotechnical investigations. One of the keys to this is getting started early. These are just different potentials for different types of excavation and construction for tunnels. We got TBM, which is a tunnel boring machine, it kind of self-explanatory. You've got cut and cover, which is you excavate out and then come in and cover the top. Pretty straightforward as well. This is a cross passage. Then you've got obviously it's contractor's choice. You got drill and blast, so you could have different solutions for different types of materials. If you've got hard rock that you're dealing with, or if you've got soft sandy soils, you're going to select different tunneling methods. So we have to be prepared for pretty much any of those throughout our alignment, because of the length of the alignment pretty much encounters everything. This is a blow up of the Pacheco Pass area with two different options shown. We've got the green one is option 2 that deepens the tunnel a bit and eliminates the need for some of the portals and those taller approach structures. We do have one fault that we're crossing over. It's not a particularly challenging area there, just because it's not rated with really high movements. This is just an example of some of the things that we're concerned with in the Pacheco Pass area. So there's this loose rock with variable geological conditions, which is typical when you're dealing in mountainous areas. There's some high ground cover, some overburden stresses that you have to worry about. None of these are things that we're overly concerned with. These are just examples of what you anticipate running into up there. Landslides as you approach the portals, just due to the steepness of the land. These are things that have to be mitigated through your design and your construction process. Obviously, when you're in remote areas, power and water is going to be a concern. This is just an example of some of the faults. This is down in the Tehachapi area. And so you can see our alignment in white crossing over these faults with active slips that are occurring. There's a number of seismic slip zones there. These are some of the technical challenges for the tunnels. There's different construction methods with short tunnels, variable, which we talked about some of these, the variable ground conditions, the groundwater, gas, if you encounter gas, and then access roads can be challenging just due to the steepness of the terrain. We did some drilling down in San Gabriel Mountains. We had to helicopter in the equipment and the personnel. It was that difficult to get to the area. So that's basically a really high level idea behind the challenges and what we're looking at with the tunnels. Land subsidence is an area that's always an interesting topic. So we're dealing with land subsidence in the Central Valley. Land subsidence is it's not, and I'll get into it a little bit, it's differentiated from settlement in that the source of the ground surface dropping is not from the overburden at the top, but it's actually from removal of the support deep underground. And in this case, it's due to water pumping wells for irrigation, for farming in the valley have depleted the aquifer, and there's a clay soil there that as you deplete the aquifer, it's like a sponge. It starts to squish down, and you end up dropping. This kind of gives you a feel. It's moving at, in the worst areas, up to 1 foot a year of drop, and so this is basically related to the groundwater pumping. So that's something we have to contend with. So here's a better view of what I was describing. This is the aquifer, and these are pumps. Now there's two different types of subsidence. One is what I call a global subsidence, which is widespread. And we're talking about 5, 10, 15 mile diameter bowl of subsidence. And that's due to the deep water pumping down low. And then you've got a local, what I call a local subsidence, which is related to shallow wells that are near surface. And you can get a bowl that's, in the hundreds of yards in diameter. What we're dealing with in the Central Valley with subsidence is a global subsidence. It's stretched out over some 15 miles. This is a little bit more description of the difference between subsidence and embankment settlement. It's induced by service load, by surcharges. You load up the ground and it starts to settle. That's what people are most familiar with. And you've got ground subsidence, which is caused by, in our case, it's caused by aquifer water loss, and it could impact a structure. Get into why we're not overly concerned with it. We first did quite a bit of research checking with local, not local, with statewide agencies and railroad. We checked with the railroads. They didn't even know about it. We checked with the Army Corps of Engineers, the USGS, Caltrans, a lot of the various different entities that have linear type systems like we have. And there were really no concerns that anyone had, except for when you get into the canals, and especially the ones that have traveling a long distance, because it isn't practical to really put a slope to a canal. They really don't have any slope per se. And so they've been affected greatly. When you start dropping over a 15-mile stretch, over 7.5 miles, you drop feet at a time, you start to have problems with your water flow. That was the only area that we saw there were mitigations necessary by the agencies. The Caltrans there was only one condition that Caltrans noted, which was up near Highway 152, which is near west of Merced area, where they've got it looked like there was some fissures. They weren't sure that it was necessarily related to subsidence, but it appeared it was. That was really the only thing that we saw. Taiwan had a problem on Taiwan high-speed rail, but that was that shallow well pumping. That was a local subsidence issue, and they were able to mitigate for that. We've checked our alignment, and we don't see any risk for shallow wells along our alignment. So as I've noted, there's a very low long-term risk to operations, and we did perform an extensive study on that, which confirmed that and indicated that. There is a potential for localized subsidence, but the risk is very low, as I noted, and it can be mitigated if it does occur. The effects of subsidence on hydrology. So if you have a floodplain and the ground is moving, that can affect the flood distribution and the flood depth over the long haul. And we've got that accounted for in our designs. The biggest effect of subsidence is you're basically trying to keep up with a moving target during construction. And so we've came up with a mitigation method that limits the amount of fill, extra fill that we would need, and basically converts our rail to move it moves along with the ground. And there's also a Sustainable Groundwater Management Act that's in place that requires by 2040 an elimination of the subsidence through recharge and management of the pumping. So we're not anticipating any problems with subsidence. Let's get into another interesting condition, which is Rayleigh waves. Rayleigh waves is in this case, some may have heard of it in relationship to seismic events, but this is more related to the actual traveling of the train along the embankment. Now, it's a particular concern when you get into soft soil conditions for your underlying ground. And what happens is that soft soil slows the reflection or the propagation of the vibration from the train. it slows that. What happens is that as the train moves along the embankment, it creates a vibration wave. That wave travels down through the embankment into the top layers of the subgrade, reflects back up in front of the train, and ends up reaching the top. It reaches the top of the embankment. What happens is, as the train reaches the speed of that reflected wave, we call it a critical velocity ratio. At 1, you're matching that wave. You don't want to match that wave, because what happens is you get a resonance effect that's kind of like the oscillation effect, and it causes some big problems for your rail. It can cause the rail to buckle if you run into that. And that is not a theoretical thing. That is an actual phenomenon that has occurred for high-speed rail. There's 2 ways of mitigating. Obviously, you avoid going that speed. You can reduce your train speed, but that's not what we want to do. You can mitigate it through design. And so you can stiffen your embankment. Now, one of the things that we're doing is, once you get to a certain critical velocity ratio of, say, 1.2, you start getting close to that critical velocity. You have to perform a very rigorous finite element dynamic modeling. These are some of the lessons learned. The biggest risk for the linear project like high-speed rail obviously is underground. Procure your right-of-way as early as possible. That helps you identify anything underground, utilities, geotechnical investigations, etc. Get your geotechnical investigations done as early as possible for the tunnels. Appropriately select procurement and delivery methods. We've got $1.2, $1.3 billion delivery methods. One of the lessons learned that we have is go smaller with your construction package. And you can specialize them, you can limit your risk, and you can also, that's a cost and schedule risk. Be careful with ATCs, which is an alternative technical concept for design build. Those are not usually very lucrative for the owner, just due to the nature of design build contracts. So be very careful about evaluating those. And then coordinate the guiding documents to line up with your contracting / delivery method. Control your design assumptions. So if you're making design assumption and you've got a designer that is making, you want to control that so that you don't have a lot of change later. Establish and maintain a robust programmatic QA oversight. So quality has got to be right up there with safety. Establish and maintain processes throughout the life of delivery. Make sure you get your processes set up in advance and manage those as you go through your program. Document, document, document. At some point, you've got to demonstrate to somebody that your certification of your system is valid. You can certify all you want and say you've certified it. You've got to be able to provide the backup documentation to show that that certification is valid. And that concludes what I've talked about. I only got into a really high level because there's so many things, but that concludes my presentation. Are there any, you guys have any questions? Everybody asleep?
No, I'm not asleep. Just have our mics off so we don't interrupt you. Thank you so much for a wonderful presentation. I have a couple of questions, but let me go ahead and just ask one of those. One thing that kind of struck me is there is quite a bit of elevated track, a lot of viaducts, and I was wondering why is that? Why is it? Is that is it only used in populated areas, or why is
No,
there that much?
that's a really good question, John. The elevated track, there's a number of different reasons why you would select elevated track. One is if you've got soft soils. It really eliminates the impact of soft soils on the structures when you do deep foundations, and all of our foundations are deep foundations. So that helps with any concerns for settlement. Also, if you got wildlife permeability, so a lot of environmental is going to be concerned with wildlife permeability, your impact on the ability of wildlife to cross your alignment. So you'd elevate there, and then also if you're in floodplains, you know, it's good to elevate because it doesn't really impact the floodplain when you do that. You don't want to impact the floodplain with your project, so you'll elevate your structure so that water can flow freely underneath. There's lots of advantages to doing elevated structures. Those are the main technical reasons why you do it. So,
Okay.
yeah.
And let me go ahead and ask: are there other questions that came up that you want to know about? Go ahead and unmute and please ask. Let me ask another one of my questions I had. Civil components are ongoing. Is there any idea when the rail components will get started?
Yeah, within the next year and a half at the most, we should be starting on rail components in the valley. We've actually got a contract ready for that. I'm not, that end of things isn't really, you know, the contracting end isn't really my thing. But hopefully very soon it should be starting.
Okay.
And that's
And
the
then,
original 119 miles, but the contract would be for the entire, to plan the entire alignment.
okay, but they would start on the 119 miles.
Right, they'd start construction on the 119. And that's our test track range, is the 119.
Oh, that'll be the test track. Okay.
Yeah, yeah, yeah. So there's a testing and commissioning phase that lasts for 18 months to 2 years that you have to go through and make sure you work out all the bugs.
Okay, great. Thomas, I see you got your hand up, please.
Yeah, so you talked about the ability to get back into service after earthquakes in some given amount of time. Given that they're electric trains, what about the power delivery to the system if it falls out? You know, if you have a drop of power supply from an earthquake, how do you handle that?
Yeah, so it depends on the event, and that area, I'll be honest with you, isn't my area of specialty. But for the operation-based event, it's a low enough event that we wouldn't anticipate power outages, but we do have phase breaks along the way as well. So, you know, if there's a complete power outage, we have backup. There is plans for backup systems. I don't know the specifics of that because we haven't gotten into that contract yet for design. But there are backups depending on the level of event, obviously. And there's some things that are out of our control. If you're relying on PG&E, for example, if they have a problem, there's not much that you can do. So it's going to depend on the level of event. But for the operation-based event, we don't anticipate power outages.
When you say backup systems, will the trains themselves actually have some amount of power on them, a battery backup? Is that?
No, it's more related to the delivery system of the power. So
Okay.
assuming we have the power delivered to the site or to the distribution points, the system that we have would be able to provide some backup, some redundancy.
Okay.
Yeah.
Okay. Other questions? Go ahead and shout it out or raise your hand as Thomas did. I'll go ahead and ask another one that I had. How has the design build project delivery worked? Is that worked pretty well. I mean, I always I always get concerned when it's design build, but
Yeah, I
I
think,
feel it's worked.
you know, my opinion, just an opinion on design build, it depends on the client. It depends on the type of project. It depends on where you are with your project. So if you're, and this is just an opinion, government agencies generally are limited to going low bid, generally speaking. And they're also government agencies. So you wear two hats. You're an owner, but you're also an enforcing agency. So it can make it kind of difficult to allow that flexibility for the design build. And you also do not want to have low bid typically for design build. You really want to emphasize more on the technical expertise and the team experience and ability with it. And it's difficult to do that when you're going low bid. Those tend to work against each other. So I think it really just depends on the project. It certainly can be done right. If it's done right, it's fantastic. If it's not done right, though, it can be fairly challenging. So I hope I answered that. It's difficult to answer, but you know, I think it's more, my personal opinion, I think it's more valuable, I think, to a private enterprise because they can have a little bit more flexibility, and plus they're relying on agencies to enforce criteria rather than doing it themselves. If when you're enforcing your own criteria, you can have a tendency, and you're also paying the bill, you can see where that can kind of
Yeah.
conflict with each other.
Yeah.
Just my opinion.
Okay. Yeah. No. I mean, it's obviously something that we all deal with. You know, project delivery and mechanisms for doing that. So
Yeah, I
it's
think, you know, we're looking at like CMGC potentially as a better option, or even design bid build as a better option for us moving forward. We are looking at our delivery method as a lessons learned element as we move forward at those north and south areas that we looked
okay.
at.
Right.
So yeah,
Is there sufficient expertise in-house for design bid build? I mean, I'm assuming the contractors would be able to build
yeah,
and bid, but is there would that be designed in-house, or is that something that would be subbed out to
yeah, that's subbed out.
engineers? Okay.
Right. The design would be subbed out, but you know, again, our lessons learned are, you know, smaller contracts and more specialized contracts. In other words, like do the type 2 overhead structures, which are all kind of similar. Do those in one contract, do your embankment in another contract, break it down to smaller segments, you know, however you want to do that. But you can still do things where you contract out the design, but it allows you to control the design a bit more. And then when you move into construction, you know you've got a dialed in product as well. It can buy you a little bit more time as well to get your underground unknowns discovered and addressed, mitigated before you start construction in earnest. If
Okay.
that makes sense. Yeah.
No,
So
that totally does. Yeah, I mean, yeah. I mean, especially if you said do embankments in one contract and then I didn't hear the other thing, but do something else in one contract, and it makes sense because, you know,
yeah,
you've learned it after the first 37 that you did. And after that, it's
yeah.
just gravy. It's like,
You know, a contractor that specializes in embankment, how well is he going to do on bridges, for example, or vice versa? You know, you can specialize a bit more from a construction expertise perspective. You know, that's one of the things we struggled with the track and systems contract is you want to keep as much civil work out of that so that you get a track and system centric prime, I guess, you know, coming in. Because that's you know, you don't want them trying to do civil work,
yeah.
you know,
Well,
and the
whenever
same thing with the civil infrastructure. Yeah. So, sorry, go
that's
ahead.
No, I was just going to say that's an important point when we're, developing documents. We got to figure out who it is that we want to bid on this. Is this primarily a civil project? Is this primarily electrical or structural, or who do we want to be uh, mainly responsible?
Yeah.
Parts
Yeah,
artists. So yeah.
there's a lot of moving parts too. There's concerns for, the downside is, you get too many contractors out there competing with each other, stepping on each other's toes, so to speak.
Yeah.
And then there's a lot more coordination, interface coordination that you have to do. So there's pluses and minuses to everything. So
Okay.
somebody's got
Hey,
their hand up.
oh, I can't tell who it is who has their hand up. Please go ahead.
Hey, John, it's Jeff.
Hi, Jeff.
So it seemed like all the pictures and diagrams and schematics you showed were double track. Is it double track the whole way, or do you have any single tracking? And so how often will the trains be going to kind of justify the double tracking?
Yeah, it's a double track system. I don't know the rate. I know that we're right now looking at having variable rates depending on the time of day, et cetera. So there could be, like early Sunday morning, yeah, you probably don't need double track. But you get into Friday evening, Monday morning, maybe you're going to need a lot of that. It's a lot more. So it varies as far as the need. But yeah, we do need the double track based on our. Again, that part of it's kind of outside my area. But based on the ridership predictions and the rates, double track is the way to go.
Yeah, I do remember reading something about double track, and yeah, articles I was reading was very much, definitely, definitely do that. But
it also provides a redundancy as well. It allows you to adjust if you have a problem on one of your tracks. It allows you a little bit of it's coordinational nightmare, but you can do some backup there.
yeah.
Looks like somebody else has their hand
Yes,
up.
that's John Jacobson. John.
Yes. My involvement basically is with the crane structure itself. Are these unique cranes to this system, or or is there a universal vehicle that design that you use from, I guess, international standard for high-speed rail?
You mean in terms of the along the for operations and maintenance? Is that what you?
No, I was just looking at the crane itself.
For the construction?
Having had to rebuild a very ancient one at one time, finding out what the international source of these vehicles are. I'm wondering, are these unique to your rail system, or are is the technology universal enough that you're using more of the international standards? How unique are you to building your own rail system?
Yeah, I think I understand. I think you're referring to the cranes that we saw in the photographs that were for construction.
No, cranes, the actual vehicle.
The train set. Okay, sorry. I wear hearing aids, so I have a little trouble understanding some of the C's and the T's, et cetera. No, yeah, what we have, and this is one of the areas that we've been challenged on the civil infrastructure design, is we don't have a selected train set yet. And so what we had to do was we had to envelope, I think it was 7 different train set potential, and the loading of that when we did our design. But it is an international, most likely, John, it's going to end up being something outside of the US. It's most likely going to be Europe or Japan, or potentially China. So it's most likely outside of the US for the train set, and a lot of the equipment for the tracking systems.
Yeah,
does that what?
Yeah.
Yeah. So does that answer what you were thinking?
Yeah. Well, I found that I was building unique things because of some of the requirements of what I work for, because there were, surprisingly just a few limited sources for some of the product that you're looking for.
Yeah, that's right. In fact, I anticipate that they will be unique. They're going to be designed for us. Yeah.
Okay, so you will have your own vehicle then.
We'll have a California high-speed rail specific vehicle. Yes. Yes. It'll be, it could be Siemens, who knows? It could be another provider, but they have to design one for us. Yeah, and that all ties together with the overhead catenary system, the rail itself, everything interfaces. So it's all set up specific. It'll be set up specifically for our program. And any other questions?
What is the interior environment? What's the noise level? What's the how comfortable is it riding in the speed rail?
I can't answer you from a technical perspective because again, it's outside of my realm, but it's going to be very, very quiet and very, very smooth. And I know that because I know the limitations on our designs. It's so strict that it basically in a nutshell, if you put a glass of wine on the table, it doesn't slosh around. That gives you kind of a picture of it. And I don't know if you've been. It sounds like you've been involved with high-speed train design and construction. Have you been on any in Europe or Japan?
I have been involved in crappy old stuff and was totally blown away by the current technology when I left Seattle and went to Portland and rode their standard CRIMAT system, which was stepping into a space age compared with what I've been working on. And,
it's very advanced, and I think it starts with the civil infrastructure. It's got to be. I mean, our embankment is like a cementitious material. It's so stiff and of such high quality. It's because of those requirements. It is going to be smooth, believe me.
Trying to sleep on the trains riding, from Seattle to Minneapolis once was an experience. Probably I wanted to do it historically because I had ridden that train when I was 5 years old, and that's a long time ago. And I felt that I was sleeping in a vehicle that was at about a Richter 3 earthquake all night long.
Well, Amtrak, a lot of the Amtrak, it runs on a lot of freight rail, and the freight rail really doesn't have, that much in the way of tolerance limitations. I mean, it's pretty rough sometimes. Yeah.
Yes. Yeah.
Any other questions? Any questions related to anything I showed? Is there anything anybody wanted more information on, or?
I'd like to have your notes if you're okay with, if you've got a PDF of those. I did want to ask, you said something interesting. Why is going under the Angeles forest tough from a third-party perspective? I just caught that and I was like, why is that? Why was that? Yeah.
Well, it's an environmental condition. It's a national forest, and to build tunnels, you need to first get your geotechnical information. But there's also, because we're under the water table there's concerns for one of the examples of why it's tough. There's concerns for potentially causing problems with the water, i.e. Could be lowering the water. It could be during construction. You don't want any contaminants, so you have to control that. And then just permitting with any national agency can be challenging, especially if you're looking at actually permitting for construction in the area. But really the biggest challenge is going to be the physical construction. You know, it's long tunnels, deep, and you guys are probably familiar with a tunnel in your area where you can see how it can really go south on you if you're not ready for it. So their tunnels are probably the most risky of all the components on a linear system like this. Just because if anything goes wrong, your schedule's blown.
Well, I'm impressed with the length of the tunnels that you have, having ridden a few tunnels in Scandinavia. But the length that you have is what, as much as 20 plus miles?
Yeah, they're not the longest in the world, but they are long. And again, you know, we have challenges, but nothing that we can't deal with. But it is going to be challenging, which is part of the fun. That's you know, the valley, Sacramento Valley is pretty straightforward when you think about it. You know, there's not a whole lot of, I mean, we ran into that subsidence, and that surprisingly actually was not really a design concern. It was really just more of it turned into a construction concern. And the problem is people see the subsidence a foot a year, and you know they get worried. Plus the graphs that you see, you know, they're logarithmic, and so it shows look at the ground here, and then all of a sudden it goes like that, and then comes back up. But that's, you know, it's logarithmic. It's not showing. You can't even see it. I've driven down through the valley, and I was like, okay, I'm going to try to figure out where the subsidence is starting and ending. You cannot. There's no way you can tell. It's way too gradual, and our study bared that out. So anyway. Anything else?
Wow. Well, thank you so much. If there's no more questions, let's oh boy, we kept you an extra 22 minutes. So thank you. Thank you.
I'm very
Brian.
impressed.
Yeah, I'd like to give
My
you
pleasure.
a round of applause. If you were here, I'd have some chocolate for you, but I might have to send that down or something. So
There's some cookies. Yeah, I like cookies.
yeah.
Hey,
Cookies.
I'd like to get some feedback from you, a debrief from you, John.
Yeah, you bet.
So if we could do that, I'd appreciate it.
Yeah, you bet. You bet.
If you
And
have time.
we can do that later on. We'll just email, and if that's good with you.
Sounds good. Sounds
Um,
good. I thought
it's-
somebody had a hand up a second ago.
I see John Jacobson still has his hand up. I don't think anybody else.
I would ask for more information on the Raleigh wave because it looks like an interesting dynamic study, but I don't think either of us have the time to explain it enough to me. So,
Well, if there's a time that you want another presentation with more detail on any of the, it was so hard to prepare for this because only an hour to talk about all of the different areas that we have. I just chose some of them because I wanted to get enough detail to talk about it. But yeah, we can always you know, I'd entertain another one that's more focused if you want. We can talk about that. Sure.
I would be interested.
I would sure like to get an update at some point down the road. I'd love to be able to tell you that Washington State is heading forward too. So we'll have to see how far behind we are.
Yeah, you know, we can help, you know, because we got some experience, and also, you know, you guys are all engineers. We're looking for engineers, so you know, get your reciprocity, and you don't even have to be ready. You could get your reciprocity afterwards. We're advertising, so you know, take a look.
Okay, good. So
It's a once in a lifetime project. If you know, this is a once in a lifetime project. Believe me, you get on this project, and that's it. It'll be the memory of your career, guaranteed.
Yeah. Well, it is. Yeah, it is a neat project. It is a neat project. So yeah. Well, thank you so much. I guess with that, we'll go ahead and say goodbye, or at least goodbye for now. And hopefully we'll have you back at some point and get an update, and maybe we'll have something to say about Washington State. And Yeah, thank you so much.
Yeah, and I appreciate you inviting me in, and I would be interested to hear where you guys are going with your efforts as well.
Yeah, yeah. Washington State is well behind. We're in those the study phase. I think I put a additional information, but we're just studying and planning at this point. So I think
Very good.
yeah, that'll
All
have
right.
to be where it sits now. So thank you.
Thank you very
Okay.
much. Have a good evening.
Okay. Thanks everybody. Bye bye.